everyone. Welcome to Learning at 11th Hour. In this video, we'll be discussing about some numericals, some very interesting numericals uh, related to transient response of RL and RC circuits. But before we get into that, there is a small concept which we need to understand. So if there is a circuit that has a network where there is a voltage source with a switch and a resistor, say it is connected to a capacitor C. Now, no matter what circuit is given in the numerical, we need to boil it down to this kind of a setup. So, how can we do that? So, if we consider this capacitor connected across the terminals A, B to be my load, then the rest of the circuit, I can simplify it and bring it down to the Thevenin's representation or the Norton's representation. So, effectively, this will be VTH and this is going to be RTH. Similarly, I can do this for an inductor also. So instead of the capacitor, if I have an inductor connected across A and B, then I can reduce the entire network that would be given in the numerical into VTH and RTH or uh, IN, the Norton's current source, in parallel with RTH. And then the entire circuit would just boil down to IN connected with RN and the inductor. So I can do this, and using this, I will be able to compute the time constant. So in order to find the time constant for an RC circuit, we know that the time constant is R into C. So this R that we are talking about, it is the resistance of the entire network, which will now, once we represent it using the Thevenin's equivalent circuit, will be equal to the RTH. Similarly, the time constant for an RL circuit would be L by R, which in this case would be Rn or RTH. In either case, both of them are equal. So we can represent the entire network using the Norton's or the Thevenin's equivalent circuit and then analyze our network. So this is the first point which we need to keep in mind. The second thing is, suppose there is a sudden switching of the source. That is, say I close this switch S at t is equal to 0. So that will actually cause a sudden change in the voltage VC of this capacitor. And if it's in case of the inductor, there will be a sudden change in the current of the inductor. But this is going to be possible only if we are applying an impulse current to the capacitor or an impulse voltage to the inductor. So if this impulse component is missing, then the capacitor will continue to be uh, maintaining the voltage which it already had before the switch was closed, and the inductor will continue to maintain the current that it already had before the switch was closed. So to say, if the switch is closed at t is equal to 0, then during switching we can say vc 0 minus, that is the instant just before t is equal to 0, and VC0 plus, which is the instant just after the switch is closed, t is equal to 0, is going to be the same. It is going to continue the voltage which it had just before switching at the instant just after switching. This is in case of a capacitor. The same thing can be considered in case of an inductor, where we can say IL of 0 minus is going to be equal to IL of 0 plus. So this is the second thing which we need to keep in mind. So the first thing was that we can draw the equivalent Thevenin's or Norton's circuit and then connect the capacitor or the inductor and consider the time constant in this manner. The second point is we need to assume that the instant just before and just after switching, during those instances, the current in the inductor and the voltage in the capacitors will remain the same. Now, the third thing which we need to keep in mind is this general expression which will help us out to solve any transient response related numericals. So that is, in a general way, we can say that the capacitor voltage Vc of t will be given as V infinite, that is at t is equal to infinity, which is the forced response or the steady state response, plus initial value, which is 0 plus, Vc of 0 plus, or V of 0 plus, initial value minus the final value. The final value again would be the steady state response into e power minus t by tau. So this is in case of the capacitor. On the other hand, for the inductor, we can say I L of t is going to be equal to I infinity plus I of 0 plus minus I of infinite t is equal to infinity by t by tau. Here, the tau is going to be equal to RC, where R would represent RTH, and here tau is going to be equal to L by RTH. That depends on whether we are representing the circuit using the Thevenin circuit or Norton's equivalent circuit. In either case, the Thevenin's resistance, the Norton's resistance is going to remain the same. So we need to remember these three things, right? This being the third point, this is the second point, and the first point being that we can actually compute the time constant in this manner. So given any numerical related to transient response, so there are just three things which we need to know. First is we need to compute the initial value. So the initial value would be V0 plus in case of capacitors, or I0 plus, which will be the same as V0 minus and I0 minus. The second thing would be to compute the final value. So the final value would actually be obtained with the help of the Thevenins, right? So or the if you want to represent it as a Norton circuit, then using the Norton's equivalent circuit. So we need to find out the final value. That is, we need to compute V infinity or I infinity, and then with the help of it, we can substitute these values in the equation. And the last thing being the time constant. So for computing the time constant again, we can make use of the Thevenin's or the Norton's equivalent parameters to find out tau. So having known these values, we can substitute them in this equation and compute our required parameters. So having understood this, let's look at a numerical that was asked in GATE in the year 2021 in the EC paper. So this is the numerical. Here, they have been asking us to compute the time after which the voltage across the capacitor will become zero. So let us first analyze this entire thing. So here we have this entire network, right? So this entire network is available, and that is connected to the capacitor through the switch. So we now need to boil it down to something like this and connect it to the capacitor. So here this would be RTH, this would be VTH, this will be the capacitor, zero point 0.6 microfarads, right? Where this is the switch, which is closed at t is equal to 0. So this is what we need to bring it down to. So the question says that initially the capacitor is charged to minus 5 volts, that is VC0 is equal to minus 5 volts, right? So now let's find out these three parameters which we just discussed. So what is the initial value here? V0, that is V0 plus, will be equal to V0 minus, which is going to be equal to minus 5 volts as given in the question. Next, we need to compute the final value of the circuit and the time constant. For both of this, we need the VTH and the RTH. So now let us open circuit this capacitor, because at steady state anyway, this capacitor will be acting like an open circuit. So we might as well remove it, right? So then the circuit becomes plus minus, this is 5 volts, this is 250 ohms, this is the current, dependent current source, which is voltage controlled, and we have the 250 ohms resistor here with the output terminals across which we were having the capacitor connected. During steady state it would become open circuit. So we basically need to find out VTH and RTH for this. So this is going to be my VTH, the voltage across this, and we need to compute RTH looking in from these two terminals, right? So to find out VTH, let's look at this circuit. Here there are two loops. This is first one, this is the second one. So you can consider I1 here, you can consider I2 over here. But since there is a dependent current source in the middle, we can consider the super mesh, right? So the concept of super mesh will come into the picture over here. So this is going to be my super mesh. So let's write the KVL equation in that case. Uh, we need to remember that this is plus minus for VR. Okay. And anyway, since we've considered this direction, we can mark the drops in this manner. Now, our VTH is going to be equal to what? VTH is effectively the voltage across this 250 ohms resistor, given as 250 into I2. So if we are able to compute I2, our job here is done. How do we do this? So let's write the KVL equation: minus 5 plus 250 I1 plus 250 into I2 is equal to 0. Now, if we look at this current source, the current direction is downwards. So we can say that in this branch, I1 minus I2, because I2 is going to come down in this way, and in this branch it is going to go upwards. So I1 minus I2 is going to be equal to VR by 500. And VR is nothing but 250 into I1, because it's the voltage across 250 ohms resistor as marked, divide by 500. So effectively I'll get 2I1 minus 2I2 is equal to I1. So therefore I1 is 2 times I2. If I replace this equation over here, then I can compute I2, right? And on doing that, the value of I2 that we get is going to be equal to, so we have 250 into 2 times I2 plus 250 I2 is equal to 5. So that is 750 I2 is equal to 5. Therefore, I2 is going to be 5 by 750 amps. Having known this, we can therefore compute VTH. So VTH therefore is 250 into 5 by 750. So let's simplify this. So here VTH is going to be 5 by 3 volts. Okay, let us now try to compute RTH. So RTH is something that's looking in from these two terminals. So how do we do that? Terminals A and B, right? So here we need to kill the sources. This is a voltage source, so we can short it. Since this is a dependent source, we should not disturb it. And to compute RTH in case of circuits having dependent sources, we need to go for the test source method. So let's connect a 1 volt voltage source over here and find out RTH. So effectively, the circuit would boil down to 250 ohms, where this is plus, this is minus, this was VR. So the branch was here. I have just turned it around for simplicity. This is VR by 500, and here there is a 250 ohms. Here suppose we connect a 1 volt test source. So in this case, our R is effectively going to be equal to V by I. So that is 1 by I, because V in this case is 1 volt. So this is the I that we are talking about. How do we compute this? So we can just apply KCL at this node. So say this is one current, this is the second current, and this is the third current, right? If we see all the three branches are parallel to each other, so the voltage across both these 250 volts is 1 volt. So therefore the current is going to be 1 by 250 through this particular branch, again 1 by 250 through this particular branch, and VR by 500. All this put together should be equal to I. So this I is entering this branch and the rest are leaving the branches. So this is the total current, and it is splitting up into these three components. Now what is VR? So 1 volt is actually plus minus. This is the polarity of this 1 volt source. But VR has the opposite polarity. The magnitude would still be 1, but the polarity is different. So VR in this case is minus 1. So I can write it as 1 by 250 plus 1 by 250 minus 1 by 500. So that is going to come down to 3 by 500. So now if I replace this I over here, we will get R is equal to, or RTH in this case is equal to 500 divided by 3 ohms. So therefore, we can now simplify this entire network and bring it to this form, where VTH is going to be equal to 5 by 3 volts. RTH is 500 by 3 ohms. Now let's look at this particular equation, Vc of t, which is V steady state plus V initial minus V steady state e power minus t by tau. So here the steady state value therefore is going to be equal to 5 by 3. The initial value we know is minus 5 minus 5 by 3 e to the power minus t by RC. Here what is R? R is 500 by 3. So let's compute RC here. So that is 500 by 3 into 0.6. So that's zero point 0.2, which is 100. And since this is microfarads, this would be microseconds. So this is going to be 100 into 10 power minus 6, of course, right? So 100 microseconds. So now this is the equation of Vc of t. We need to compute the parameter t for which this voltage is going to be equal to 0. That is what our question is. So here we've been asked to find out the time after which the voltage across the capacitor becomes 0. So here we just need to substitute Vc of t as 0 and put t is equal to the rest of it. We have to make t the subject of this equation. So what we have here is 5 by 3 plus minus 20 by 3 e power minus t by tau. So if we are able to solve this, we will be able to compute t, which would approximately be equal to 0.132 microseconds. So I hope you'll be able to solve this. You just have to take this on the other side. Minus 5 by 3 is minus 20 by 3 e power minus t by tau. The 3 goes, this is 4. So 1 by 4 is equal to e power minus t by tau. Here if we take natural log on both sides, so we will get the ln of 1 by 4, that value should be equal to t by tau. So generally the natural log of fractional values will be negative. So therefore this negative value on the other side, the right hand side of the equation would also go away. So it will be tau ln of 1 by 4. That is going to be equal to t, where the value of tau is going to be equal to r into c. So this is how we need to proceed with any transient response numericals, regardless of whether it is for a capacitor or an inductor. So there are three things which we need to remember. We need to compute the initial value, the final value, and the time constant of the circuit. And in doing that, we have to make sure that we boil down the network into a simplified form. So in case of a capacitor, this is how it would be, right? And in case of an inductor, we have to do it in this manner. So how can we do this? We can boil it down to a simplified form using the Thevenin's equivalent or the Norton's equivalent representation. In order to compute the time constant, the resistance which we use would be the resistance of the network, which in this case is going to be the Thevenin's resistance. I hope you'll be able to solve more such numericals related to transient response of RL and RC circuits. If you have any queries, please do feel free to post it in the comments below. And do subscribe to this channel for more such videos. Thanks for watching.